the workshop on 3D reconstruction. In particular, we want to present, analyze, and discuss several mathematical methods for 3D vision and 3D printing, trying to make a link between the two communities that are not always in contact. So the program is available on the web, but has also been distributed yesterday to all the participants. So there is only one main change. That is, the first talk will be given by Jakob Andreas Bærentzen instead of Adrien Bartoli, and Bartoli will replace Bærentzen on Thursday afternoon. So we have organized the virtual coffee room in such a way that we can split into two groups. There is one group staying in the main Zoom room, and a second group will go, if you agree, in the coffee room. So the idea is that the first speaker of the session remains in the main room, and the second speaker of the session moves to the coffee room, so that if you want to chat or discuss something with the speakers, you know where they are. Okay, so you will receive an invitation from the manager, and if you agree, then we switch to the virtual coffee room. Okay, this at the end of every session. I think it's so with respect to the organization. Thanks to the INDAM for hosting the streaming on YouTube on its channel, and I think we can start in a couple of minutes. I also thank the organizers for setting up this interesting program, in particular Grégoire Allaire from Polytechnique, Jean-Denis Duroux from IRIT, Silvia Tozza from the University of Naples, and Emiliano Cristiani from IAC CNR in Rome. So I hope you will enjoy the meeting, and as we wrote, you can share the information regarding the YouTube channel to everyone, because the link is easily accessible to everyone. You don't need to be registered. So if you have students or if you have collaborators who would like to attend part of the meeting, then you can send them the link to the YouTube session. Okay? There is no limit. Everyone can access. Okay. So just wait a couple of minutes, because with respect to my clock, we are a little bit in advance. If you have questions regarding the organization, you can ask me. I have another information for the speakers and for everyone. For the speakers, the information is that we are planning to publish a volume with the main lectures. If you agree, you should send a paper regarding your topic in a reasonable amount of months. So typically, so the end of this summer. And the INDAM, the Institute for Higher Mathematics, has a series with Springer, and all the volumes are in that series. So if we collect about 12 papers coming out from your talks, we can publish this volume in 1 year approximately. This is the timing of the proceedings for this kind of volumes. And what else? For all the participants, there is another interesting information that if you miss a talk, you can probably get back to it accessing the YouTube page. So after the meeting, we are going to put all the recordings on the YouTube channel of the Institute INDAM. So if you just miss a couple of talks, then you will probably find them there if the author has authorized us to publish this on YouTube. Okay, so I think it's all, and we can proceed with the scientific program. And it is my pleasure to introduce the first speaker, Jacob Andreas Bærentzen, from the Applied Mathematics and Computer Science Technical University of Denmark. And the title of his talk is Reconstruction from 3D Point Clouds, Subtle Deformations and Tiny Features. So please, you have to share the PDF.
Yes, thank you. Thank you for the introduction, and I hope you can all see my my slides. So I'm going to talk about reconstruction, and going by the names of the attendees, at least some of you are well aware of many of these things, but I've decided to give a relatively accessible introduction to how we can get 3D structures, 3D shapes out of point clouds, and then move towards some of our more recent research findings. So first of all, where do these points come from? Well, generally they come from optical acquisition, at least that's what I'm considering today. There are numerous methods for optical acquisition of 3D models. These range from laser scanning, structured light scanning, structure from motion, to time of flight, and other methods. And many of them rely on the fundamental principle of triangulation, that if you know two lines in space, for instance, the line from a laser and a line from a camera, then you can find a point in the 3D shape, because you know that at the illuminated dot that you see through the camera, the line from the camera crosses the line from the laser. And usually when we reconstruct a 3D shape, we divide it into two phases. One is the reconstruction of points from the images, and the other is the reconstruction of the 3D surfaces from the points. So I will let other people focus on getting the points out of the images, and I'll focus on how we can reconstruct 3D surfaces from the points. And just to give you a brief overview, this is basically my talk. So I'll start by covering some methods for 3D reconstruction, both combinatorial and volumetric at a very high level, but just to give basically an overview of the main concerns and the main trade-offs. And then I'll discuss a topic that we looked at some years ago, which is basically casting the problem of non-rigid registration as a smoothing problem, something that we can do before or even after we've actually combined the point cloud into a mesh. And finally, I'll talk about some recent work where we've been using graph methods to capture very thin structures from 3D point clouds. Okay, so first of all, why is this not a trivial problem? Why can't we just create a 3D model very easily from a point cloud? Well, if the point cloud is really a height field, so you basically have 2D points with elevation, it is pretty straightforward. Although the very simple method that you might consider first, which would be to simply take a point and connect it to all of the neighbors within a given radius, that's not going to work, because if you do that, you will get interesting crossing lines, and besides that, the minimal loops that you'll find will not all be triangles. So generally, we're trying to triangulate the points. However, there's of course the 2D Delauny triangulation, where basically you can find triples of points that have an empty circumcircle, and then form a triangulation out of these. So assuming the points are in general position, meaning that that no 4 points lie on a common circle, then in fact this is unique. So in the example here, I've just trimmed away some of the boundary triangles, but otherwise this is just the result of Delauny triangulation. Now, unfortunately, this only works if you have essentially 2D points. So the problem that we are facing is the slightly more challenging problem of getting a reconstruction from a point cloud where there's no projection direction that will turn our point cloud into a 2D point cloud where we just have the elevation of each point. So this is basically the problem. Now, how do we go about that? Well, there have for many years been a number of methods to do so. So basically, in combinatorial 3D reconstruction, what we're trying to do is to connect points to form triangles. But the caveat is that we tend to require a manifold triangle mesh, which basically means that all of the triangles all of the edges must be incident on at most 2 triangles. So if you're inside a surface, the edge should be incident on 2 triangles, and at a boundary, the edge should be a boundary edge and incident on only 1 triangle. Also, the triangle should form a single loop around each vertex, meaning only that if you have 2 pyramids that share an apex, this is not allowed. This is not a manifold configuration. So to simplify the problem, many methods start from the Delauny tetrahedralization. So just like the Delauny triangulation in 2D, Delauny tetrahedralization transforms points into a simplicial complex where the circumcircles of the simplices have an empty, is empty. And Sassal and Giesen provide a very nice overview, I think, of the methods for Delauny-based reconstruction, both methods which are based on Delauny tetrahedralization and also Delauny triangulation. But still, it's a little bit involved, and many people have been looking at another family of methods for reconstruction. And these are the volumetric methods for reconstruction. So the trouble with connecting points is that in the presence of noise, in the presence of outliers, it might be difficult to construct a manifold surface. And of course, you also see the noise very plainly in the reconstructed surface. So the volumetric methods, on the other hand, are based on the idea that you want a characteristic function that maps a point in space to the range from, say, 0 to 1, or a different range. It doesn't really matter. What matters is that you want the characteristic function to have the property that if the value at a point in space x is less than a threshold tau, then the point is inside. If it's greater than tau, then the point is outside. And if it's exactly tau, then the point is on the surface. Now, usually this function chi is stored in a tabulated form in a volume, meaning a voxel grid, so a 3D image. And from this tabulated version of chi, we can now find an isosurface, we can find the surface using isosurface contouring. So for isosurface contouring, I prefer the dual contouring family of methods. I think Sarah Frisken was really the first to discuss these, but there are many publications talking about isosurface contouring, or using the dual contouring methods for isosurface contouring. And very basically, the idea is that if you have a voxel grid where some of the voxels are inside, and some of the voxels are outside, you find all of the inside voxels, and then you find all of the faces of inside voxels that are shared with outside voxels. So this gives you the picture in the middle. And these faces are then stitched together to form a mesh, and you can finally project the corners of the little cubes onto the iso surface. producing the output mesh. So if you triangulate that, you get a triangle mesh. And I prefer this because there's more freedom to place vertices when you use dual contouring than with marching cubes. So we typically get nicer meshes. Okay, but how do we obtain chi? And I think that for a talk such as this, it would be wrong not to briefly discuss the Poisson Reconstruction method, which I think was a very elegant proposal for how to do volumetric reconstruction. So the basic idea here is that if we have a point cloud, well, we have points in space, and at each point we can estimate a surface normal, and this surface normal it can be, or the surface normals can be construed as a vector field. So basically, given a point in space, we can look up the normals associated with the points and thus find a vector field. Of course, in many parts of space, the vectors will be 0. But what we now want is that the gradients of our characteristic function chi, they should match this vector field. Now, how do we find a chi whose gradient field matches the vector field? Well, all we have to do really is to apply the divergence. So if we do that on both sides, then we get the Laplacian of chi should match the divergence of the vector field, which is a scalar field. So we immediately see that it's been reduced to a Poisson problem. So this simple insight led to the Poisson reconstruction method by Kashtan, Polito, and Hoppe, and it's been improved in many ways by the authors since then. So, for instance, one objection that one might have immediately is that, okay, it's good and well that we obtain a function chi whose gradient field matches the vectors, but how do we know that there is an isosurface that passes through the points? And in fact, we don't know. The surface that we extract by isosurface contouring will, of course, be an approximation to the points. But what we can do is we can find for all of the points what are the values of chi, and then we can take the average value of chi and use that for isosurface contouring. Besides, some of the many improvements that have been made to the method have, for instance, focused on making sure that the surface interpolates the points as well as possible. Okay, so that's Poisson reconstruction, but there are still some observations that I'd like to make, and one of them is that that of course in the basic version we obtain a globally defined chi, and we don't really need that for volumetric reconstruction. In fact, for volumetric reconstruction, maybe we would prefer not to have a globally defined characteristic function, but a characteristic function that's only really defined in the vicinity of our point cloud. Because after all, if we have a big hole in the surface, a globally defined chi would close the hole effectively, because an isocontour of a scalar function such as chi would always be a closed surface. Okay, so if we don't want chi to be global, we could, for instance, express it in a way that's very common in reconstruction or in the point set surfaces literature, simply as a partition of unity, as a sum of basis functions, one for each point, weighted by a weight function that decays away from the point itself. So, for instance, chi could be the sum of these weight functions wi times phi I, where wi is simply a Gaussian centered on the point in question, and phi is just the distance to the plane that's given by the point and the normal that we've estimated at the point. Usually, by the way, to estimate these normals, we'll take the point cloud and compute small local covariance matrices, and then it's basically the smallest eigenvector of the covariance matrix for the point in question that we use as the normal. Okay, so this is how we can reconstruct or this is how we can find a characteristic function that will be defined in the vicinity of the point. And in fact, this is very similar to the method called floating scale surface reconstruction by Fuhrmann and Gösele from 2014. They added many more details to the method, and in particular, what they added was the ability to use your confidence in the point to control the weight, meaning that low confidence points would not ruin your reconstruction. And they were able to get very precise results with their method. What I'm showing you here is a much simpler approach, but one that I teach students and find to be quite effective actually at volumetric reconstruction. So here we have a point cloud. It was a point cloud of an owl, or a statue of an owl, containing 666,000 points. And we reconstruct this in a volume with the dimensions that you see on the right, producing a bit more than 1 million triangles. Now, the Python code that you see on the left is literally the code that was used for the reconstruction. It's changed only slightly for legibility, but it works exactly in the same way. So all we have to do is to loop over all of our points, and for each point we define, we find the point position and the normal. We can use that to obtain our mapping, our weight function and the distance from plane. All that we otherwise have to do is map from the grid positions to the space of the points. And then we can, in a local neighborhood in the voxel grid around each point, we can then store these, the values of phi and the values of w. So one point to make here perhaps is that instead of explicitly computing the sum for each point, what we're doing here is we are computing the sum for all of the voxels, because it's far more efficient in this way. Since we don't have to find the points in space, we only have to apply the values to the voxels. And then we have to normalize the sum in the end when we are done. And then finally, we can compute the mesh by isosurface contouring. So of course, it's interesting to compare this method to one of the combinatorial methods. So for this example, I picked a method called scale space meshing by Julie Dignier and co-workers from 2011. And I think this is an interesting method. It's based on the observation that if we smooth the points, essentially creating a scale space of the point cloud, it leads to an easier reconstruction problem, and also one where more points will be used, because if they are projected onto a smoother surface, it becomes easier to triangulate them such that we use all of the points, or at least many of the points. And then the reconstruction method that they use is the ball pivot algorithm by Bernardini et al., which I'll not go more into details with, but basically the idea is that you roll a ball on the point cloud, and points are connected into triangles if the ball doesn't sort of fall between them as you roll it, starting from a single edge. Now, if you run ball pivot algorithm directly on this point cloud, which I tried, you won't get a very good result. But if you use scale space meshing, it actually works nicely. But there are many other combinatorial methods that could have been applied here. So this is just an example. But one important point about the method, though, is that once we've used the smooth point cloud to do the reconstruction, we put the points back. So this method doesn't change the position in space of the points. The final mesh contains the points where they were originally at. And if we look closer, we can see that the difference between these two meshings is not enormous, but it's clear that we can see some artifacts on the scale space meshing reconstruction, because in essence we can see the structure of the scans. And this is gone in the volumetric reconstruction. You can also see that the volumetric reconstruction extends a little bit further out. In effect, it extrapolates a little bit from the point information. And of course, if we look very closely, the differences in the produced meshes become very clear. Now on the left, you see scale space meshing, and you can very clearly see the structure of the scans, the lines containing the scan points. On the right, you can see that the dual contouring has produced a relatively nice looking triangle mesh. And what's not visible is basically the structure of the scans, the overlapping subscans. Looking a little bit more closely at the, if we look at the shading here, we can see that that there's some noise, of course, in scale space meshing, which is gone using volumetric reconstruction. So in effect, we are not over smoothing, we're not overfitting. We could, of course, have used a finer resolution volume grid in order to capture even the structure of the scan. However, of course, this is one of the things that people like about volumetric reconstruction, that you don't capture these errors. On the other hand, and we could, of course, just apply, for instance, the quarter of a century old method called Tobin smoothing to remove the noise from the scale space meshing. So this is just a brief comparison of scale space meshing and a very simple volumetric reconstruction method. Okay, moving on to a more specific problem that motivates why I am increasingly in favor of combinatorial reconstruction methods, maybe. There's a problem that we've often encountered when we try to reconstruct from point clouds. And it's, of course, based on this fact that we cannot really scan an object from an entire object in just one scan. We almost invariably need to scan from multiple directions. And what you see here is the 3D model of a toy house that was scanned from 3 directions. And it's very clear that the scans don't perfectly overlap, despite having been rigidly aligned using the iterative closest point method. If you look very closely at the slight, I think it's a cornice in the center, you see the little inset on the right, and here the reconstructed mesh clearly contains a lot of noise. And in fact, this noise is due to the fact that the alignment hasn't been perfect. You can see in some places we see far more green than blue, and in other places more orange than green or blue. And this is, of course, simply because one scan is a little bit in front of the other scans. And that's what causes this noise. And it's not terribly mysterious. It's simply that optical scans tend to differ by a slight deformation. The camera lens that we use is not a pinhole, and probably some lens distortion is unmodeled. That's my guess would be that's the main reason. But also many materials are slightly translucent, which impacts reconstruction. And finally, of course, some objects are deformable. That would not be the problem in the case of the toy house. But if we are scanning a botanical object, for instance, outside, then slight deformations would be a problem. Now, of course, in this case, we could simply remove the noise by smoothing, but that would wash out features. So the scheme that we propose is to smooth the reconstructed mesh, but keeping the subscans as rigid as possible. So going a little bit more into details with this in a small toy example, let's say that we have 2 sample sets, the red samples and the blue samples. So let's further assume that we have some noise. But in fact, the noise is just a difference in translation between the two sample sets. Now, if we create a curve by connecting the samples, as you see, the dotted line is just a connection of the samples, then it has this high frequency noise, which is in fact just due to the shift between the two sample sets. It's very far from the ideal data. And we could fix this problem easily enough simply by smoothing the reconstruction, simply by smoothing the dotted line. But if we do that, while the Laplacian smoothing, so just basically replacing points with averages, the Laplacian smoothing will tend to remove the curve from the features, the sharp features that you see. So what we're proposing to do instead is to smooth the deformation itself. So if you take the original curve and you find the Laplacian vectors, the displacements that will make it smoother, you can smooth those displacements in such a way that the smoothing of the displacements on the red points you'll only smooth the displacement over the red points for the red points, and for the blue points you will only smooth the displacement of the blue points with respect to other blue points. And of course, if we're dealing with a triangle mesh, or rather if we're dealing with a 3D scan, if we have a mesh connectivity for the combination of all of the scans, we use that mesh connectivity when we find the displacements. And then for each of the scans, we assume that we have another connectivity. For instance, we could have done the Delauny triangulation, because typically you can do Delauny triangulations of the individual subscans. So we then could smooth the deformation field computed from the global mesh across each of the subscans. So that's the principle. It's formulated a little differently in the paper from 2014. So basically, here's an energy where the first term is the difference between the target displacements and the displacements that we seek. And the second term is basically you multiply the displacements D onto the matrix M, which then takes the difference of displacements at adjacent vertices on each subscan, and thus penalizes if you have differences between the displacements at adjacent vertices. And then alpha is a parameter controlling the stiffness. So minimizing this energy with appropriate choices of alpha, we are able to implement basically the same method that you saw as the toy example before. And this means that if we look very closely, this is the detail from the toy house. If we just smooth, this is what we get. But if we apply this method with some rigidity, we get a far better reconstruction. And here they are side by side. And here you see the original scans, and here you see the registration. So what's been done here is that we've computed the displacements from graph Laplacians, in turn computed from a mesh reconstructed with the Co3NE method. In fact, we could also have computed the displacements just using centroids of the k nearest neighbors from the combined point cloud. This is a little slower because, well, at least in our example, we recomputed these centroids in each iteration of the method, but also produces a nice result. There are a few caveats. Oh, well, here's the owl. And there are a few comments and caveats to this method. So first of all, you can't just apply it if you have meshes that subscans in arbitrary positions of space. This assumes that you first have a good rigid registration, and of course only limited deformation. If the features are very far apart, this will not work. It's only if if the meshes differ by a slight deformation such that you get this high frequency noise that this method applies. On the other hand, you could apply it even after combinatorial reconstruction, but it can also be applied if you simply construct a neighborhood graph of the combined point cloud. So this is basically a way to sort of remove the last tiny bit of high frequency noise without simply blurring away details. But there are even harder problems that we sometimes confront, and that's what I want to talk about now. If we have an object such as, for instance, a tree, and in fact I was given such a point cloud by a colleague a few years ago, then we are in a way out of luck, because when the distance between the points becomes relatively large compared to the size of the features, almost all of our reconstruction methods start having trouble. So the question, and the final question that I'll talk about today, is how do we even approach such problems? And the idea that we formulated was to basically see if we could find the structure of the tree, essentially the center lines of the branches, or the skeleton, if you will, of the tree, and then reconstruct the shape of the tree from that. So to go about this, we wanted to come up with a method that only really relied on the neighborhood graph of the point cloud. So just connecting points to neighboring points, could we find a skeleton? I know there are also several methods for skeletonization of pure point clouds. We've compared to some of these and found that our method works better. There's at least one very recent method that we haven't compared to yet, but we haven't really been able to obtain their software. But let me just describe our method. So given a 3D model, so in this case we use a mesh as an example, just to make it easier to see what's going on. And I just want to first explain an alternative approach. So let's say that we take this mesh and we find the eigenvectors of the Laplace Beltrami operator. Then the first non-constant eigenvector, sometimes called the Fiedler vector, will look like this. And now, just as for the tree, I can construct a graph out of this mesh simply by finding the graph given by the edges of the mesh and the vertices. Okay. The next step now is to use an algorithm similar to Dijkstra's to basically visit all of the vertices in the order of the Fiedler vector value. So just a graph traversal starting from the lowest value of the Fiedler vector and then moving up through the mesh. And then we can freeze the front of the Dijkstra traversal at specific time steps, and that's what gives these colored curves. And it's perhaps important now to note that these are separators. We cannot pass from one side of the mesh to the other side without going through these colored curves. Okay, so we can create a skeleton simply by contracting the colored curves. In fact, what we do is we expand them slightly to also include the closest vertices which are not on the colored curves, and then we contract them. So of course, this is neither more nor less than a simple implementation of a read graph. We've just refactored the idea of read graphs a little bit and found vertex sets that correspond essentially to an isocontour of the function that generates the read graph, and then we contract those contours. Now, this is not a perfect skeleton. So one thing we then proceeded to do was to run this method with a bunch of eigenvectors or a bunch of other functions. They don't have to be Laplace spectrum eigenvectors. And if we do that, we get a bunch of skeletons, and they look increasingly hopeless. But there are nice features in all of these skeletons. And one advantage of doing things in this way, of obtaining a set of vertices that form a separator on the mesh, is that we can combine these separators from different runs, so from different rows of this image. If we do that, in fact, we get a somewhat better result shown here. So what's happened is simply that we've taken the separators, the vertex set shown as colored curves, and we've combined them using a set packing approach such that no two separators overlap, and we weight them according to a quality scheme. Now, the skeleton that we obtained was actually not so bad for this horse model, but in many cases we found that even this method makes it a little bit hard to find even more subtle features than the ears of the horse, like digits of 3D models typically. And basically the challenge here is to design good functions that can be used for this, for read graphs basically. So we tried to come up with another method for finding the separators, and I'll just briefly describe it. This work, by the way, has not yet gone through peer review. It's under peer review, but there's an archive publication that I refer to here. Okay, how do we compute the local separators? Well, the basic idea is that you take an input graph. So now I'm going back from a mesh to a neighborhood graph, just to show the principle on a simple example. And then the local separators are separators of subgraphs. In practice, what we do is we start at vertices, and then we grow clusters of vertices. And when the cluster, the front outside the cluster, when that breaks into two connected components, then we have a separator, and then we contract it again to make it minimal. And in this case, we find a bunch of separators, and you can see they are the components with the same color. In some cases, they're as small as a single vertex. In some cases, they are clusters of vertices. But in all of the cases, you cannot go from one part of the shape to a part on the other side of the separator without passing through the separator. Okay, so if we then contract the separators in the same way as before, forming a skeleton, this is what we get with a simple example. We can now form the neighborhood graph of the tree and apply the same method. I just show it on the horse first. Here are the local separators, and here's the skeleton, and here are the local separator-based skeleton and the eigenvector skeleton. And you can see that while both are actually quite acceptable in this case for some applications, around the ears especially, the local separators capture a little more details than those from the eigenvectors. Okay, and now we can get the skeleton of the tree simply by forming a neighborhood graph of the input points. We simplified the neighborhood graph a bit by contraction, and then we computed the skeleton using the local separators method. Of course, to reconstruct the tree, we need also some idea about the thickness of the branches. And there's actually a famous formula by Leonardo da Vinci, which basically says that the cross-sectional area of daughter branches would sum to the area of the mother branch. So if we take area literally, then delta in the formula should be 2. in fact, delta might vary a bit, and actually that we found that it's a fairly good model near the trunk, but when we get close to the smallest twigs, the cross-sectional area of small branches and the even smaller branches, daughter branches, is not so big, and the formula doesn't quite hold, or at least delta becomes very big. So a bachelor student who looked into this, she first of all attached, because the skeleton contained some disconnects where branches hadn't been properly scanned. So she reconnected some of the disconnected branches and then modeled the tree, essentially finding how delta changed through the graph, and then reconstructed the tree using the method known as convolution surfaces, where you basically sweep a sphere along the edges of the graph. And with that in place, we're able to get this reconstruction of the tree. So you might wonder, how close is it actually to the point cloud? And of course, not all points have been captured. So if we use cloud compare and look carefully, you can see that, well, you don't have to look carefully. There's a bunch of points which have not been captured. But if we go into the point cloud, we can see it doesn't appear that main branches are missing. So in some places, it looks like maybe the points are noise, maybe the points are tiny twigs. It was a winter scan of the tree using a LiDAR scanner. So presumably there are no leaves, but probably many small twigs that simply couldn't really be captured. But most of the branches and even the small branches have been captured. So we were fairly content with this result. And while there are many other methods for reconstructing botany, it seems that this is a nice approach which does not require a lot of prior knowledge about the botanical structure that you are looking at. So here's a view without the mesh of the error of the point cloud. So you can see that that for the bigger branches, the tree, the reconstructed tree, is a little bit bigger than the branches, and when we are near the little twigs and leaves, the red points indicate where the points are outside the branches. And that brings me almost to the end. I should acknowledge my collaborators. So Ebba Delvik from DTU Wind Energy provided me with the tree scan, and Ida was the bachelor student who basically put it together. Eva Rodenberg is my collaborator on skeletonization, and Florian Gavrilovic is the grad student who did the early work on non-rigid alignment. And looking forward, where do we go from here? Well, I think it's interesting that surface reconstruction is both a trivial problem and extremely hard in some cases. I think that combinatorial methods and graph structures point to one important future direction. Another direction, though, that I didn't have time to go into, is that we could also try to use some of the new results pertaining to differentiable rendering to optimize shapes directly to match input images. So basically sidestepping the whole issue of points. And in fact, some of my colleagues have recently published on how to use differentiable rendering for reconstruction from structured light. And with that, I'm done. Thank you for your attention.
Thank you very much, Andreas, for your interesting talk. So I think that we have time for questions, and I have seen that there are 2 questions in the chat. Probably the best way to manage the question is that the people make the question directly to the speaker. So Ron Kimmel has a question. So can you please read your question, or if you want, I can read it, but I think it's better that you activate your audio. Ron, are you there?
You needed to unmute me. Now I can talk.
Okay, thanks.
Okay, so my question, you showed the volumetric reconstruction with the Poisson solver, and then in the reconstruction you have shown holes in the surface. How do you get these holes? I mean, it should be at least there should be some, I mean, the hole seems to be something that goes beyond the marching cube or something like that, if we are looking at volumetric structures.
Yes, it's a good point, and one that I glossed over. So the holes are simply because where we don't have points, the basis functions are not added to the volume. So we just have the initialization volume there, the initialization value there, which is actually not a number values. So this means that whenever the polygonizer tries to create a polygon, a quad, in an area where at least one of the corners has an undefined volume value, it'll simply throw away the quad. So it's trivial, but it's a subtle detail that I glossed over. So thank you for the question.
So we have another question from Emanuele Rodola.
Yes, can you hear me?
Yes.
Yes.
So this is about the thin structure reconstruction. And so first of all, very impressive results. I find it very surprising that you can get, well, such good results with that method. So good job. So I'm aware of a work, a very old one. I think it was ICCV 2013 from Daniel Kramers and collaborators. I think the first author was Jan Stumer, so I might be wrong, I don't remember the title, but that was on reconstructing thin features by incorporating connectivity, well, connectivity constraints into an optimization problem. And the result was a convex energy with convex constraints. So they were actually able to find the global optimum to this problem. And they showed very good results, like very similar to what you showed. They had applications in medicine, like reconstructing blood vessels. So this kind of stuff. So I was just wondering, so first of all, this was just a pointer for you. So, but if you are already familiar with the work, maybe if you can elaborate on the limitations, because at the time I had the impression that the problem was solved.
Yeah, so honestly, I cannot at the moment recall that specific paper. There are several other ways in which you can reconstruct digital botany, either using skeletal information or maybe using inverse procedural modeling that I'm aware of, but not this particular one. So I'll have to apologize, and I think I'll take a look, and then perhaps I can make a comment offline. So thanks.
Okay, thanks a lot. Thank you.
Thanks. So there is another question from Grégoire Allaire. Please activate your audio.
Yes, thank you, Maurizio. Can you hear me?
Yes.
Okay, so thank you very much for these very nice talks. But I was, wondering that in the last part of your talk, all domains were simply connected, like a tree or like your horse. What would happen if you have to reconstruct a domain with many small holes? I typically think about lattice structures or,
So the skeletonization method does not care. It would work fine even if there were disconnected, if there were many disconnected pieces. But you do touch on an important problem, which is what if we have a thin hole through a structure?
Yes.
So these local separators that we use to find the skeleton, they would see they would find loops around the hole, and this means that we would then obtain a skeleton bit which represents the hole rather than an exterior structure. So this is also an excellent point, and one that I did not address. I think that this is true of many skeletonization methods, that in fact, if you have interesting convexities, the skeletonization methods would and should also capture these. But it's still, of course, a problem that if you happen to have a 3D object where you want a skeleton, but in places you also have some maybe spurious concavities,
yeah,
what do you do? In fact, there's one of the standard test sets, a dragon 3D model has exactly such an interesting interior structure. I think the best we can do maybe is to apply some morphological operation to the object to make sure that small internal cavities are removed before we run the skeletonization. But yeah, I think that's my answer.
okay, thank you.
Okay, thank you very much for your talk again. And I think we have to proceed with our program. So the second speaker is Alexander Bronstein from the Department of Computer Science at Technion, Israel. And the title of his talk is Geometric Approach to Matrix Completion.
Good morning, can you hear me?
Yeah.
Perfect. So thanks for the introduction and thank you for the invitation. Can you see my screen?
Not for the moment.
Let me just share my screen.
You have to share the screen.
Yeah.
Okay, now it's better. Thanks. Perhaps, oh, okay, full screen, perfect.
Yes. Okay. So first of all, thanks for the invitation. At the time I was invited, I hoped I would be physically in Rome, but unfortunately this didn't happen. So this is the next best setting, I guess. So I would like to share with you some recent work that I've been doing with my PhD student Amit Boyarsky and Sanket Fiedler in the domain of matrix completion. So you might ask why the heck I am showing you matrix completion in this workshop dedicated to 3D geometry processing. But essentially all this line of works that I've been doing in the past year and a half on matrix completion is actually a corollary of what we've been doing with functional map approaches to intrinsic shape correspondence. And I will try to show you how this problem maps to the standard tools. I won't have the time to mention all the background on functional maps, but those who are familiar with these tools and with these notions will immediately see a lot of resemblance, and I will try to make some connections briefly. So let me start with the general formulation of a matrix completion problem. I assume that I have some domain, or actually two domains. Let's call them row space and column space. Let's take the canonical matrix completion problem, a recommender system that Netflix introduced some time ago. So if you don't know, Netflix was, before it was actually doing video streaming, they were actually sending DVD discs with movies to rent, and they had a certain set of users and a certain set of those DVD titles, and they, in order to optimize their logistics, they wanted to predict which movies each of the users is likely to want to watch next. So the row space will be the space of users, the column space will be the space of titles, in this case, the movies. And we would like to assign some scores, some ranks to the titles for each of the users. And obviously, Netflix nowadays has, I don't know, millions of titles probably, and has many millions of users. And a lifetime wouldn't be sufficient to watch all those movies, obviously. So this matrix cannot be sampled completely. What we are given instead is some sparse set of measurements. So let's say, let's call the matrix M, and Mij is the measurement of a recommendation that user I gave to title J. So I actually watched the movie and I gave it some rank, some score. Okay, and what I am given is this incomplete set of measurements that is supported on some set of indices that I'm going to denote by S. Okay, and the goal is to estimate this entire matrix of scores that I'm I'm going to denote by X, and with some abuse of notation, I will be just doing this element-wise product with the mask matrix S. So wherever I have the measurement, I would like the reconstructed matrix to match those measurements, and wherever I don't have measurements, I would like to complete it somehow, right? And of course, this recommender system is just a toy example. It's very important for Netflix, obviously, but I think more important applications are, for example, drug treatment recommender systems, or I would like to see how a certain drug binds to specific targets and rank them accordingly to recommend the best treatment for some disease. So because we have these sparse measurements, I can write this problem again as minimizing some loss between the observed measurements and the reconstructed matrix. Obviously, this problem is underdetermined. There is an infinite number of ways to complete the matrix outside of the measurement support. So I need some sort of regularization, some prior on X. And a very common prior that has been used in this literature of matrix completion is to assume that the matrix has low rank, or at least approximately, that the singular values decay sufficiently fast. So with this prior, of course, the number of degrees of freedom that exist in this problem are significantly reduced, and we have some hope to reconstruct the matrix in a meaningful way. Okay. The problem is, obviously, as you well know, that the rank is an intractable prior. The rank measures the biggest dimension of linearly independent columns or rows of the matrix, and there is a combinatorial number of possible combinations of vectors that we can take. So there are standard approaches. I'm just rewriting the problem in a Lagrangian form without the constraints, or just putting some penalty here. Mu controls the strength of this penalty of the rank. There are standard approaches to solve this rank regularized matrix reconstruction problem. One of the approaches is a convex relaxation. So the rank, you can think of the rank as a pseudo-norm that counts the number of non-zero singular values in X. That is, of course, an intractable norm, right? But we can relax it into something convex, something that is the closest norm that would be already convex. The closest norm is called the nuclear norm. It just sums the singular values of a matrix. And you can think, of course, of the analogy between the L0 norm and the L1 norm here, just generalized to matrices. And it is a very important norm on matrices. And due to seminal works by Candes and Recht a decade ago, there is actually a very efficient proximal descent type of an algorithm that uses SVD shrinkage. It essentially takes the SVD of the matrix, it shrinks the entries, and then reconstructs the matrix. And in this way, we can actually solve this non-smooth optimization problem, a convex optimization problem, with the rank replaced by the nuclear norm of X. Okay, so this is a very famous family of approaches. They are computationally intractable for large matrices because SVD is a very costly operation. It cannot work if our matrix has a dimension of millions by millions. Another approach is to enforce the rank by factorizing the matrix. So if I factorize my matrix X into two factors of a product of two factors Y and Z transpose, and I demand that the Y factor is narrow and the Z factor, Z transpose factor is short. So I just put K columns in Y and K rows in Z transpose, then obviously the product matrix has an upper bounded rank. So this is a very simple way to enforce rank, low rank constraints. However, the problem becomes intractable. I mean, it becomes non-convex. We can try solving it, but there is no theoretical guarantee that we're going to get any meaningful solution. And a more extreme approach to this problem is what is called by the name of deep matrix factorization. Instead of putting low rank factors, just 2 low rank factors, we can actually put k full rank factors. So y1 to yk, whose product is our matrix X that we are trying to reconstruct, this representation is overdetermined. We have an infinite number of ways to reconstruct the full space of n by m matrices using the product of these factors. But why would one ever prefer to do this representation? We have more optimization variables, and we have even more degrees of freedom than in the problem that we started with. The justification for this deep matrix factorization is the dynamics of the gradient descent algorithms that essentially implicitly regularize the rank. So if you solve this problem with any variant of gradient descent, you will actually realize that only a small number of singular values of this product is going to be promoted, and the rest are going to be attenuated. And this is basically caused by the trajectory that gradient descent chooses in this space. And these results are due to Aurora, a relatively recent paper from 2019. There are some assumptions on the type of the loss function that needs to be that we need to choose, and of course these simple loss functions satisfy those assumptions. So essentially, we overparameterize the problem. We have more degrees of freedom, but in exchange we get an implicit rank regularization. So we don't need to explicitly put the rank penalty anymore. Okay. Now I would like to move to a more interesting setting. So a rank, of course, is a very meaningful algebraic prior, but it is totally ungeometric. And I would like to take advantage of some additional geometric priors or geometric information that we might have, or we typically have, in this kind of application. And basically, this idea to introduce geometry into the problem dates back to Kalofolios and co-authors from 2014. And then I think probably one of the state-of-the-art approaches is due to Monty and other co-authors from Michael Bronstein's group from 2017. So the idea is that in the case of the Netflix problem, for example, we have some meaningful geometry that we can put underneath the user space. The users, for example, form some social network. And if, for example, I'm a friend of somebody, so I'm close to that somebody in the social graph, it is reasonable to assume that my tastes will be similar. So whatever that somebody liked in the column space, in the space of movies, I would like as well. So we can use this geometric information to better propagate the scores. And the same about the column graph. For example, if I liked a movie of a specific genre or several movies of that genre, probably movies that are similar in the column space are something that I'm going to score similarly as well. So we can use this geometric information. I'm assuming that we are going to be given two graphs, the row graph and the column graph, GR and GC, respectively. And now we can think of our matrix as a signal that lives on this product graph, on the product of GR and GC. Okay, and I would like to use this to introduce a prior on the matrix G. And our prior will be that X is band limited on G. It's band limited on the product graph G. Band limited means in the signal processing jargon that the Fourier transform of the matrix on the graph has energy that is concentrated in the low frequencies. So the eigenvalues decay fast. Okay, and I will assume for now that GR and GC are given, they are known. So these are indeed the graphs on which the matrix X has this nice band limitedness property, and I will abandon this assumption in a few minutes. Okay, so just to introduce some simple math, in order to express this band limitedness prior, I would like to eventually express it in the spectral domain. I will assume just assume that I have some Laplacian that I can associate with the row graph. So if I denote the potentially weighted adjacency matrix by AR on the row graph, and DR will be the diagonal weighted degree matrix, the DR minus AR will be the graph Laplacian. And there are many other ways to define meaningful Laplacians on a graph. This is the simplest one. I will do the same for the column graph. Okay, so just the subindex R and C will distinguish between the two graphs. The Laplacian of the product will be just the Kronecker sum of the two Laplacians. This is a nice separability property because the product graph is also separable. So the Laplacian will assume this nice separable structure. Okay. Now going back to the prior that I want to express on this product graph. So saying that X is band limited on G, I don't really mean band limited that the frequencies are sharply zero above some cutoff frequency. I would just like to penalize high frequencies. So this can be done by penalizing the Dirichlet energy, by demanding that the Dirichlet energy of X on this product graph is low. And it means that X changes slowly with respect to the metric of the graph. And this Dirichlet energy can be written as this inner product between X and the Laplacian of G of X. And the inner product, of course, is with respect to the metric of the graph. And because of this separability property that we had before, it can just decouple into two Dirichlet energies on the product, on the row graph and on the column graph. So just this trace, the sum of these two traces is what we are going to get. Okay, so now we can write our matrix reconstruction problem with these two additional geometric priors as our data term that we had before, plus these two Dirichlet energies on the rows and on the columns. Now, I'm not putting the rank regularization anymore because the rank regularization is going to be implicitly obtained by using gradient descent in the overparameterized representation, which I will introduce shortly. But here, X, the parameters are just X for now. Okay. I would like now to transform this representation of my unknowns into the spectral domain. So I will decompose the row and the column Laplacians into their orthogonal decompositions, denoting by phi and by psi the corresponding eigenvectors, orthogonal eigenvectors of the row and the column Laplacians, and lambda r, lambda c are going to be the diagonal matrices holding the eigenvalues. Okay, so in this formulation, I can write X as this product of phi, C, psi transpose. So C is just the representation of X with respect to this pair of orthogonal bases. Now, those who are acquainted with the formalism of functional maps will immediately recognize that even in terms of notation, it is very similar. I'm on purpose using the same letters that we typically use in papers on functional maps. So if we don't think of X as a signal for a moment, but we actually think of it as an operator, a matrix is an operator, a linear operator that maps between one graph to the other, between the column space to the row space, for example, then we can represent this operator with respect to this pair of bases. And the C will hold the Fourier coefficients, if you will, of this operator. Now we want this operator to be band limited, or to be nice and smooth with respect to the metric of these two spaces. So we can think of C as a Fourier representation of this functional map. Now this is our energy term. With some algebraic massage, after we change the basis, we can just transform it into this, obviously substituting the expression for X. And because phi and psi they diagonalize the corresponding Laplacians, we get this very simple expression for the energies. Obviously, lambda. So the penalty now has a quadratic form with diagonal matrices. That is obvious because we are working with the eigenbases of the Laplacians. But now just think what this penalty does. The bigger is the frequency, the bigger is the eigenvalue, and the more penalty we are paying for having energy in that frequency, which is expressed by the matrix C. So it actually makes perfect sense. So now I just wrote the matrix completion problem with this new parameterization, with the parameterization C, and we will call it spectral geometric matrix completion, or SGMC for short. Okay. So far, we assumed that the graphs GR and GC were known, and this is a little bit a naive assumption. So even if I have, let's say, a social graph of the Netflix users, and I have some other meaningful graph relating between the movies, there is no guarantee that these are indeed the graphs that gave rise to the matrix that I am observing. It might be a process that was created by a different geometry. The actual geometry is latent. I think we can reasonably assume that these graphs are somehow related to those latent graphs, but the actual graphs are not known. So I would like to depart from this assumption that GR and GC are known and actually modify these graphs. So I would like to learn these latent graphs, to reconstruct them together with the unknown matrix, rather than blindly relying on the given graphs. So the way I'm going to do it, and again, this is very much related to what we've been doing with shape correspondences, I'm going to learn the modified basis for the graphs. So instead of just taking phi and psi from my input graphs, I'm going to learn phi prime and psi prime that is going to be obtained by an orthogonal transform of the two original bases. And the orthogonal transform is parameterized by two matrices P and Q. Okay, so in this formulation, I can now write the problem with respect to C, my original matrix, but now I'm also allowing to learn the two bases, two transforms of the original basis, P and Q. Okay, this is how the data term and the smoothness terms appear now. And I also need to introduce some additional penalties. I would like the matrices at least to approximately, the new basis to approximately be orthogonal. So these transforms P and Q need to be approximately orthogonal. And I also may demand that the new basis still approximately orthogonalize the two Laplacians, so I don't really depart too much from the geometry of the original graph. So this perfect diagonalization would be possible only if the two graphs were isomorphic, but I might demand little deviation from isomorphism of the two graphs. And you can see, basically, we have been doing quite an extensive work in this domain, trying to use these approximate diagonalization methods for shape correspondence. We are just using, with the copy and paste, more or less, these methods for matrix completion. And I will show you in a few minutes some results. This method performs surprisingly well. So essentially, what we got, just look at how the data terms appears here. We are optimizing with respect to C, P, and Q. Look at this product, P, C, Q transpose. We can think of it as a deep matrix factorization of our original matrix X with these three factors. So it's deep matrix factorization with depth of 3. The only difference is that we have a different basis here, right? The basis phi and psi. So it's DMF with respect to a different basis, to actually a very natural basis that stems from the input graphs. So it's DMF in a different basis. Plus, we have these geometric regularization terms. Now, from ablation studies that we did on real problems, it appears that only the smoothness terms are really important. The orthogonality and approximate diagonalizations are less so important, because actually the graphs that we are given are very far from probably the graphs that really give rise to the data, and therefore we can depart from them without ruining the performance of the problem. So essentially, this SGMC is nothing but a form of DMF with a different in a different basis and with an additional geometric regularization term. Okay. Now, there was a very curious work, and I think very influential as well. It is strikingly simple and extremely powerful for solving shape correspondence problems that goes under the name of zoom out, which was introduced 3 years ago by Simone Melzi and Emanuele Rodora and Max Ovsianikov's group. Basically, the idea was that you can solve shape correspondence problems by first looking at very low frequencies and then gradually increasing resolution, and the problem became much more stable, and you can really solve it with a few lines of code. So we can introduce something similar here. We can demand that our signal that we are reconstructing, our signal X, is smooth, is band limited within a subspace. So we can filter it by spectral filters FP and GQ that are written here. And following the zoom out loss, these spectral filters can be just chosen to be diagonal filters. So just a diagonal for a few frequencies that are set to 1, and then the rest of the frequencies are set to 0. And then we demand the sum over different P's and Q's, different cutoff frequencies, increasing cutoff frequencies, the sum to be minimized by our optimization problem. So this is the zoom out loss that was used in the original zoom out paper, and we can use it here. If you now look at what this loss produces, we can think of it as a combination of separable filters that together give a inseparable filter on the product graph. So if we use this loss, it doesn't satisfy the conditions of Aurora's theorem. So we don't know if the theory guarantees implicit rank regularization. But first of all, our experimental results show that we still get rank regularization, actually, when we use gradient descent. And then also we have some theoretical thoughts how to extend the theory to this case, but we still don't have a formal proof. So we'll show you some results. First of all, on recommender systems. So these are just standard benchmarks for recommender systems. SGMC and SGMC with the zoom out loss is reported here. The errors are mean squared errors on these matrix completion tasks. And what you see here, first of all, this MC is the rank regularized matrix completion using the convex relaxation that Candes and Rechter introduced. And then there are several other algorithms from the literature. DMF is the vanilla DMF in the original domain, and other approaches are from the literature, like, for example, this RGCNN that Monty introduced. It's a quite complicated neural network on graphs that estimates the matrix in a factorized form, and FM is just the functional map approach without the overparameterization and without implicit rank regularization. So essentially, we can think of SGMC as a combination of these FM and DMF approaches, as I already mentioned. First of all, you can see from these results that SGMC outperforms other methods consistently on these several benchmarks, on the recommender system benchmarks, which I think is not necessarily a praise to the method itself, but actually I suspect that the other methods, and SGMC probably as well, is not really fully exploiting the information that is contained in the graph. So I think we should try harder to take advantage of this information. These are addition. So we have these additional results with drug interaction benchmarks, and we have a few more interesting benchmarks that we've been working on. But basically, this drug interaction benchmark, it is exactly like the Netflix problem. The rows are drugs, the columns are targets, and we would like to predict. We would like to complete the matrix. We would like to predict how a drug interacts with the target. So this data set, the targets are enzymes. There are 3 evaluation settings, 1, 2, and 3, as you can see here. One is pair prediction, just completing the matrix and evaluating how well you did for pairs. You just select random set of pairs and you complete from that random set of pairs of drugs and targets. Setting number 2 is drug prediction. So you have missing rows. You have zero information about some new drug. Can you predict how it will interact? And then we have missing columns, the target prediction. So suppose you have a new disease, let's say COVID-19, for example, how well the drugs are going to interact with that particular target. So we have it for enzymes, we have it for protein-coupled receptors, we have it for ion channels, basically different types of targets. It's again, I might be talking about it with confidence, but I have no idea about the biology behind this. But basically, you can see, at least numerically, that without few exceptions, SGMC outperforms the other approaches. Basically, I'm just reporting other approaches from the literature. We didn't run their code; we just competed on the same benchmark. And in some cases, the numbers are much higher. So the criteria here is the area under the ROC curve, the area under the precision recall curve, and the RMSE. Again, standard error criteria that biologists use in this benchmark. I would like to show you a few plots comparison to DMF. Basically, we did this spectral reparametrization and we introduced geometric constraints, but how well it performs compared to the vanilla DMF. So here are a few examples showing when this geometric extension is important. When we have a matrix of decreasing rank, so the lower is the rank, the easier is the problem, the less degrees of freedom we have. So you see a comparison between DMF and the vanilla SGMC version without zoom out loss. When the matrix becomes low rank, actually the SGMC completion error drops significantly. And here we have a 2 order of magnitude difference. So basically when the rank is high, the methods perform about the same. But when the rank is low, when the matrix is regular, to start with, this geometric approach actually gives much better results. And same about matrices with a fixed rank and different training set density. So basically the size of the support of the training samples that was given. When the training set density goes down, the reconstruction error of SGMC grows less fast than DMF. Again, we have difference by 2 orders of magnitude, with all the rest of the conditions remaining the same. Another important example, and this is actually very important in real recommender systems, like the one with the drugs that I showed you briefly, is the cold start. So in the cold start, we have rows or columns that have very few entries, and how many few means. Here we are showing 3 examples. We have just 1 rating, 5 ratings, or 10 ratings in the columns, and this is the number of cold start users in the Netflix problem. This is movie lens 100K data, again films that users recommend. And you can see that SGMC and SGMC with the zoom out loss actually significantly outperform DMF in this cold start problem. So I would like to conclude. Again, it started as a corollary of our work on intrinsic shape correspondences, but actually grew into an independent research direction. So basically what I presented is a simple, I would even dare say trivial extension of deep matrix factorization using spectral formulation. It performs better, and now I'm more convinced because we tested it on many more benchmarks, performs better than, I would say, most of the other methods that are reported in the literature. It includes an implicit graph learning by learning those left and right factors, those bases. We do implicit graph learning. And it has useful interpretations related to shape analysis. Unfortunately, again, I wasn't able to show full connections. I hope some of the people, at least in the audience, appreciated the relations to the functional map framework. When we tried to present it in the paper, the reviewers said that it was irrelevant. We should kill it. But I think this is the most important and most interesting and beautiful connection. When I say that we have a simple technique, I really mean it. So this is Python implementation of the basic SGMC method using PyTorch. You can see it's really simple, and it outperforms other methods that have thousands of lines of code. So if you are interested in the paper and in the code, I have these links here. And thank you very much for your attention. We'll be happy to answer questions.
Thank you very much, Alex, for your interesting talk. I have seen that on the chat there are two questions. So the first one is from Emanuele Rodola. Please activate your audio. So,
Emma, I cannot hear you.
okay, Emanuele, you can go on.
Okay, sorry, Alex. Actually, you already answered my first question, but I have another one. So if you can go back to the minimization problem. So I kind of get lost with a bunch of symbols, even though I'm familiar with what you're saying. Yes, this one.
Mm-hmm.
So I'm wondering, do you really need to optimize for matrix C? And you just get rid of C, and well, you declare that your C is P times Q transpose.
Yeah, I see what you're saying. Interesting question. So I think if I remember correctly, in one of the works. Well, so first of all, the formal answer, I have no idea. We haven't tried it yet, but I suspect that it could be possible. It could be actually maybe even beneficial. Either just remove C, or fix it to something fixed that you don't optimize over. There are some works in the deep learning community that try to fix some of the layers of a network to, for example, to be an FFT, let's say, or some sparse matrix but fixed matrix, and then all the network adjusts around that matrix. Typically, this factor is put in one of the output layers. I think Nadav Cohen did something like that, if I remember correctly, in the context of DMF. I'm not sure. Maybe I'm confusing it with something else. But basically, there are some works where one of the factors is fixed, right? So what you're suggesting essentially is to fix this factor, not necessarily to identity. It might be something else, a more meaningful matrix. Not
exactly.
Necessarily.
Yes.
Yeah, I think it would be very interesting. It would be very, very interesting to try. Absolutely.
Okay, so we can go on with the second question, Ron. Are you there?
Okay, sorry.
Okay.
So again, I missed the point, but Alex, what is the relative size of P and Q, and I would assume also of C with respect to the size of X? I mean, you assume here some low rank in this dual basis space, and practically in your examples, what is the relative size of P and Q? I mean,
okay. It's a very important question when it comes to dealing with actual real matrices that might be very large. So first of all, in all the benchmarks that we worked on, the matrices were relatively small scale, so it's thousands of entries. We could work with the full decomposition of the Laplacian. We could take all the harmonics and work with that. But because we are imposing this band limited property, so essentially the energy in the high frequencies is practically null. We can truncate the representation the same way we typically do when solving for shape correspondence. The shape might have millions of vertices, but we are solving for C that is a few hundreds by few hundreds. So we can truncate to the first few K eigenvectors of each of the Laplacians, right? So phi and psi could be truncated bases with a few hundreds of harmonics, and P and Q will be correspondingly a few hundred by few hundred. C will be few hundred by few hundred. So that, of course, leads to a practical problem. The eigendecomposition itself, there are efficient methods if you want to obtain the first few hundred lowest eigenvectors and eigenvalues of a sparse matrix like the Laplacian. It is tractable for millions of entries. Sure.
So you assume that P psi would be a low rank the same as psi.
Well, so basically, yeah, by doing this truncation, of course, we introduce some bound on the rank. The actual bound on the rank that DMF is going to promote is going to be lower. So it's an additional rank regularization, if you will. But we actually never tried it for so big matrices. At least we know that it is possible from shape analysis problems where we deal with very large shapes, but we never tried it in. We don't have any interesting benchmark that has such a big matrix.
Okay, thank you.
Okay, so there is another question from Simone Melzi.
Okay, so my question is, looking at this approach for a different application, do you think it is possible to start without any initial information, so without M, and look for the relation between two graphs, like looking for the solution X, starting without any initial information?
Well, so at least in matrix completion, if you don't have any initial information, basically what are you going to complete? It's just guessing something, right? But what you could do, and this is I think a very important problem in the drug interaction or any recommender system, I guess, is basically how do you sample? So here you are given a sample and you are trying to extend it to propagate that information on the product graph. But now I ask you, where would you put your next sample to decrease the reconstruction loss, right? And basically, in that case, you don't have any information. You don't have that out of sample performance. You don't know the ground truth to compare to, right? So basically, maybe this kind of completion without any measurement, this is something that could be very useful here. And we are actively working on this. I hope we will be able to show some results very recently.
Okay, because I think this could be related with the map tree approach that is connected with zoom out, starting without any initial map. You can start with different initialization, trying all the small functional map that could be enumerated, and then you can perform you can build a tree and explore the tree and find the best solution with respect to some regularizer or some final laws that you want to optimize for.
No, of course. But eventually, remember that we would like to complete a signal, right? We would like to have some measurements, but knowing where to measure, like for example, if I'm given measurements only in one, let's say, of the connected components of this graph, I would like definitely to sample it someplace where I don't have samples that will reduce my loss there.
That's it. Thank you.
Okay, are there other questions or comments? No, so I have one for you, Alex. So in terms of mathematical properties, I mean, the results from a numerical point of view are very impressive. But do you have something that shows theoretically that the method has a higher speed or has lower complexity or has some general properties that explain why it's better than other methods?
Yeah. So first of all, you asked about several things. So let me try to address all of them in some arbitrary order. So first of all, regarding theoretical properties, at least for some of the losses that we tried and some of the losses that we are currently working on, like for example, ranking losses or classification losses, not only MSE, we know that Aurora's theory holds. So we know that we're getting explicit rank regularization, right? So we brought the problem into that formulation. The fact that we changed the basis still makes the theorem hold. We don't have this theoretical result yet for the zoom out formulation. So that is a shortcoming. So we see that it works that way, but the analysis in that theorem is not applicable. It needs to be extended. So that is regarding the theoretical properties. So we know that we're getting both this geometric regularity and implicit rank regularization when we use a gradient descent for the solution of this problem. So for that we have theoretical guarantees. Regarding the complexity is higher compared to DMF, to the vanilla DMF, because you also need to do the initial eigendecomposition of the Laplacians, right? So that is an additional step that costs you more time. But basically, what the examples show is that it pays off in the reconstruction error, that these geometric properties actually help in real data. Of course, if we have data that are generated from a graph, that is obviously a very good approach. You can actually show that it will be much better than just assuming low rank. But it seems that real data also obey these assumptions, which is obviously not a non-trivial observation. It's not ours, but it's a non-trivial observation.
Okay, thank you very much for the answer and for the talk. So now there is a virtual coffee break. So the first speaker should remain in the first room, so the one that hosts all the talks, and the second speaker should go to the coffee room, so that if you want to make a chat or to ask other questions to the speakers, you know where they are. You will be invited by the